Hello, everybody. Thank you for coming. My name is Timur Doumler. I'm developer advocate at JetBrains. We have a booth right over there. Please come and visit us there. We have a C++ quiz. You can participate. You can win power banks and talk to us about C-line and other C++ stuff. It's fun. Right, but I'm going to be talking about C++ and safety. And why am I talking about safety? Well, turns out JF over here actually nerd sniped me into doing this talk on Twitter. I was like, hey, what should I talk about? And then JF suggested I should maybe talk about safety and security. So here I am. Let's see how this is going to go. So obviously, it's been a hot topic lately in the community. And we had a keynote yesterday, a brilliant keynote by Sean Parent about this topic. So I'm going to try and not to repeat too much of what Sean said. I think I have a somewhat different take on some of the things there. So hopefully that's going to be useful. For those of you who are watching this talk afterwards on YouTube, I recommend you watch Sean's keynote first, because I'm going to try not to repeat the stuff that he said. Before I actually dive into the more controversial parts, I want to establish some terminology, because so I have to say a disclaimer, I'm actually myself not a safety and security expert at all. I don't know what I'm doing here. I was kind of observing this debate, and I decided I need to figure out what's going on. And then, it was suggested that maybe a good way to do this would be to give a talk about it at a conference. So here I am. And I was trying to figure this out. And one problem that I faced is that the terminology wasn't clear. Everybody was talking about safety, but safety meant very different things to different people. So, and there were also these other terms like security and correctness that were kind of floating around, and I didn't have a good definition of those things. So I thought maybe a good way of starting would be to figure out what these things mean. So there's a paper from a bunch of people on the committee, on the C++ committee, about safety, and they offered this definition of safety. Safety is an emergent property of systems, measured statistically and regulated by policy. The prerogative to decide if something is safe is usually reserved to governmental organizations. So that might be a useful definition. It is defining safety as a property of a system. There is another definition here on Wikipedia. If we try and be a little bit more specific, there's this concept of functional safety. So functional safety basically means that a system is functionally safe if in response to different inputs or events that happen, it does the right thing and it doesn't cause any harm. Right? So that's, again, a property of a system. And if you talk to people who work in safety and security kind of critical applications, of which I am not one of those people, you see that there's a lot of regulation there. There's a lot of kind of fine-grained, how do you say this, classification around this, right? So you can define different safety hazards. They can be to internal or external causes. You can differentiate between malfunctions, environmental causes, misuse by the user, right? So there are different regulations for those things. And that's all safety. And then security actually deals with intentional misuse. So basically an attacker who intentionally tries to do harm or get into your system, right? So that's kind of the distinction between safety and security. So it's kind of intentional misuse or an attacker trying to intelligently do something bad versus unintentional factors from different sources. And so, there's a lot of material on this. Again, I'm not an expert, so I would like to refer you to other sources, like, for example, Andreas Weiss, who is sitting, I think, here somewhere. Here you are. Andreas was on our podcast recently, CppCast, where he explained all of this. It was a fascinating episode, so you can check this out. He also last month did a talk at C++ Now on this topic, like how do we actually develop safety critical software. So again, I recommend you check that out. I'm not going to go into that here because not what I'm doing at my job. I want to kind of zoom in on another type of safety, which I call language safety. So I don't want to use safety kind of unqualified. I always want to use it in some kind of qualified, more specific way so that we know what we're talking about. And so in the system, we have all of these layers, right? We have the environment, we have the user, we have the programming language the program is written in, and underneath we have some kind of operating system this runs on, and then the hardware, right? And so, because we're at the C++ conference, I really want to zoom in on the programming language level, right? And so when we're talking about the programming language, we can talk about language safety, and we can say that a program is language safe if it exhibits no undefined behavior. And this is a definition that I kind of arrived at that other people use, which I think is useful in this context. And then we can consider a programming language safe if it's impossible to express a program in this language that has undefined behavior, okay? So that's kind of the set of the terminology I'm going to be working with. And we can break down language safety further into memory safety, which is what a lot of people have been talking about lately. We can break it down further into type safety, bound safety, lifetime safety, initialization safety. And then there's threat safety, and depending on the source, some people kind of throw that into the same bucket as memory safety and say that's kind of also a part of memory safety. Some people say that threat safety is actually separate. So again, you have to be careful kind of how different people classify these things in a different way. There's arithmetic safety. There's another aspect which is not very often talked about, which I call definition safety, which you're going to talk about later as well. So we're going to dig into this a lot more throughout this talk. But before I go there, I want to talk about another term, which is correctness. So this is another term that's being thrown around quite a lot. And I was trying to find a definition for correctness. And here's one that I found. Correctness is the state of being free from error. Okay, well, that doesn't tell us very much, does it? But then again, just like with safety, like you can kind of specify that a little bit more, and instead of just using the unqualified word, you can be kind of more specific. And there is a term, functional correctness, which is slightly more useful. And functional correctness is always defined with regards or relative to a specification, right? So a program is functionally correct with respect to a specification if for every input, it produces output that satisfies that specification, okay? So that's hopefully straightforward. But as it turns out, it's actually very difficult to decide whether a program is correct. So here's a talk that I really liked by Marshall Clow from cppcon 2019, where he was talking about how to implement std midpoint, which is, it's a fantastic talk. So he just talks for an hour about how to implement a function that takes two numbers and computes the number in the middle. And so here's a possible implementation. Is this implementation correct? No, why not? A plus B could overflow. But then what does the specification say? Maybe the specification says overflows undefined behavior. Maybe not. What should happen? Should it wrap? What should it do, right? What should it do for infinity or none or all sorts of other edge cases, right? What should it do for floating point, integer, unsigned, signed? There's all kinds of different cases there, right? So are these all specified, right? And do we then implement the specification correctly? It turns out that the first problem is actually to get the specification right. And if you have a complete specification, you pretty much already have the implementation. It's kind of almost equivalent to actually implementing the function, right? So that is one problem. Another problem with this is that, well, if a function returns the correct result, that assumes that a function actually returns. And as we all know, that's undecidable. That's the halting problem, right? You cannot prove whether a function even returns anything in general, right? Obviously, you can for simple cases, but there's no general algorithm to do that. So what we can do is we can split functional correctness into total and partial correctness. And we can say total correctness is the property that we just talked about. It returns the correct output. But then we can factor out the halting problem and say, well, there's also partial correctness. We don't know if the function returns, but if it does, it returns the correct result, right? And so that's something that's a little bit easier to reason about. You can prove partial correctness with different formalisms. There's the Hoare logic. There's all kinds of formal proofs, verifiable languages like Daphne, which is what Sean was talking about yesterday. But for a real-world C++ program, you can't, in general, prove that property either. And so with that, we come back to safety and security. So JF, I'm going to mention your name quite a few times, did a fantastic keynote last month at C++ Now, where he was talking about all of this stuff. And it kind of helps to bring all of these terms together. And like one kind of central thesis in his talk is that there is no functional safety without security, and there's no security essentially without language safety. So I can encourage you to watch your talk if you want to know more about how we arrive at that. And with that, we can kind of draw a kind of Venn diagram, right? So we can say, here's a set of all language-safe programs. And for C++, it's going to be a subset of all programs that we can express, right? Because we have UB, so there are programs that we can express that are not language-safe. that have UB. And within those programs that don't have UB, there is a subset of secure programs, right? You can have no UB but still be insecure. For example, you can transmit the password in plain text, right? That's not a secure thing to do. And then within the secure programs, we have another subset, which are these functionally safe programs. That means they're not going to do any harm, depending, like, no matter what kind of input or other thing you throw at them. And then within that subset, we have this really elusive subset of these correct programs, and that's kind of what you're really after. And it turns out that, none of these properties really imply that the program is actually correct. And there's lots of examples of programs that don't have any UB or any like obvious thing that you could diagnose in any automated way, but they're actually not correct. And so here's an example. So what we want to do here is we have a floating point number and you want to add 1 to it like 100 million times. What does this function print? Or what does this program print? What would you expect it to print? 100 million, yeah, it should print 100 million. What does it actually print? It prints, yeah, less than 100 million by about an order of magnitude. Why is that? That's floating point writing error, right? Like you have a big number and you like add numbers to it, and then the kind of difference in magnitude between the number that you have and the number you add to it becomes bigger and bigger and bigger, and at some point, kind of the number you're adding to it is just outside of the floating point precision that you have, right? And so that is an error that can occur in practice. Like I heard an anecdote that there was some kind of missile that landed in the wrong spot and destroyed the wrong house or something like this because that happened, right? So that is definitely not a safe program in that case, but there's no UB, right? So you cannot prove that this is wrong, and static analyzer will probably not bark at you. It's just you didn't know about floating point rounding errors, right? So you should have used the Kahan algorithm, which does this correctly, compensates for floating point errors at runtime cost for this particular problem. And there's lots of things like that, right? You might be using the wrong units. That's famously the reason why the Mars climate orbiter crashed, right? So we can mitigate that by using a good unit library, right, that enforces that. But you might not know that that exists, right? Or you can mix up operators like plus, equals, and equals. Again, typically, no tool is going to catch that. So those are errors that don't really depend on a programming language at all, right? And so you can mitigate those things by doing testing, design by contract. Other programming languages like Ada have kind of interesting things in that direction. But that has nothing to do with undefined behavior, right? So what I want to talk about is undefined behavior. So why are we talking about this? And so as Sean Parent mentioned in his keynote yesterday, there has been a lot of pressure recently from governments and other organizations to move away from memory unsafe languages. So here's the report from the NSA that says that vulnerabilities are frequently based on memory issues, and some examples involve overflowing a memory buffer and things like that. Microsoft and Google reported that about 70% of vulnerabilities they see are due to memory safety issues. And the fault is C and C++. We're using C and C++, they're not memory safe languages, and that's why you're getting these vulnerabilities. And the solution is to move away from these languages and basically move the whole software community away from C and C++ and towards memory safe languages. So there was the consumer report, which also repeated this pretty well-proven number, I think now, that about 70% of vulnerabilities are due to memory issues. And again says that to change this pattern, the industry must shift, and we need to move away from C and C++. Here's a fantastic talk by Jim Radigan from cppcon last year, which drills a little bit more into these, like 70% of vulnerabilities come from memory issues, like what are they? And these are kind of the ones that you would expect, right? Use after free, out of bounds, et cetera, et cetera. So that talk kind of links them to actual vulnerabilities. So that's a very, very interesting talk. There was the White House report that was saying, well, we really need to rethink our cybersecurity strategy completely. It's not just the US. The European Commission also is drafting a Cyber Resilience Act. And so why are governments pushing so hard? And there seems to be this kind of shift from being concerned mainly about the critical infrastructure, things like the energy grid, aerospace, or things like that governments care about, to basically all the software out there, right? The software that we are writing, or all of us are writing. And so I obviously can't know why that is, but my best guess is that obviously governments are interested in securing critical infrastructure, but because the software in critical infrastructure is using other software like Boost or whatever, we kind of need to, in order to secure that infrastructure, we need to secure everything. We need to secure all software out there. So I think that's kind of at least part of the motivation where this push comes from. And that led to lots of ruminations in our C and C++ community, lots of news articles like this. We have a huge C and C++ problem. We don't want to deal with it. So you've probably all heard all of this noise that's been going on. A lot of talks and conferences lately have been focusing on this topic. Like the last few C++ conferences I went to, there was a huge focus on safety issues because it is a big relevant problem that we as a community need to address. And all of those publications and news articles make that very clear. So last month at C++ Now, Shalek Ruth gave a keynote. It had carbon in the title, but he wasn't just talking about carbon. He was talking about security more broadly as well. Great keynote. One of his statements there was that safety places invariants or limits on program behavior in the face of bugs. That's, I think, a very useful way of looking at it. Then, I already mentioned JF's keynote. JF works in automotive. They actually write safety critical software, so he really knows what he's talking about. That's what they do every day. And he really drives the point home that we really need to do something about safety in C++. Okay. And so I don't disagree with that at all. But what I want to do in this talk is kind of offer maybe a view from somebody who doesn't work in the safety and security industry and looks at it kind of a little bit from the side and looks at it maybe a little bit more critically and kind of tries to question some of the things, right? So this is kind of what I want to do in this talk, offer this kind of perspective. You might find it useful. You might tell me afterwards that I'm all wrong on all of that stuff. That's totally fine. I'm happy to have that conversation. Hopefully we will all learn something, which is kind of the goal here, right? So I was looking at all of this and I was trying to make sense of it. And I noticed a few things. Like one thing that I noticed is that pretty much all of these publications, whether they come from governments or news websites or wherever, they're all saying C/C++. So they all throw C and C++ into one bucket. All of them, all the ones that I've seen. I'm really curious why that is. So I was really, then I was trying to dig and I was basically, you can do this yourself. You can go on Google and look for vulnerabilities per language. And every source that I could find that actually places C and C++ in different buckets and gives it different numbers for those programming languages looks something like this. This is from a report from WhiteSource from I think last year, relatively recent. C is single-handedly responsible for almost as many vulnerabilities as all other programming languages combined, whereas C++ is like way down the list, right? Like it has fewer than Java, JavaScript, which are memory-safe languages. So I think that's kind of important, right? That's kind of not being talked about too much at the moment. But I also don't find that surprising, right? Because C++ has a lot of facilities that are safer than C, right? C is a very unsafe language, and C++ has decades of evolution to move away from those things, right? So in C, a lot of these problems are due to manual memory management with row pointers in one form or another, right? And in C++, you basically don't need row pointers anymore at all. We have all of these things to replace them with. We have unique pointer and other smart pointers. We have variant instead of union. We have string instead of char pointers. We have stat function instead of row function pointers. We have containers instead of arrays. We have a span instead of like a pointer and a size. We have MD span now instead of like representing multidimensional arrays with like pointer to pointer to pointer and all of these things that C people do that I always get wrong if I have to do them. And like in general, we just don't have to do any pointer arithmetic, right? Because you have range-based for loops, you have views, you have ranges, you have all of this good stuff. So C++, I don't think anybody can argue that C++ is a much safer language than C because of those things. However, there are, of course, a few problems. Those safe features are not 100% safe, right? Because all the containers, they have a subscript operator, which has a narrow contract. If you call it out of bounds, you will have undefined behavior. It's not bounds checked. Unique pointer has get or release, which gives you the row pointer. So you can get it out, right? And so all of these safe APIs, they're good, but also they're not mandatory, right? Because C still mostly compiles with the C++ compiler. So all the old stuff still works, all the unsafe old stuff. And we don't have a switch to turn it off. Right? It's been attempted to do something like this with epochs, which didn't really fly. We don't know right now how to do this, how to have a switch that turns off all the row pointer C stuff. But then even the safe features are not 100% safe, right? As I said, we have subscript operator and stuff like that. And so let's look at this in a little bit more detail. So why is that? So we have this Venn diagram here again, right? And so we said that a program language is safe if it doesn't let you express programs that are not language safe. And so one question that I have been hearing a lot from developers is, why don't we just make all of this UB just ill-formed? Because nobody likes UB. So why don't we just make it go away? Why don't you say it's an error? It's a really good question. And there's no easy answer to that question, but I'm going to try and kind of drill down into this a little bit more. But I think essentially, like with everything in engineering, you can do that, as we know from memory-safe languages, but there are trade-offs, like with everything in engineering, right? And here, some of the trade-offs are safety versus performance, safety versus backwards compatibility, which are very important properties of C++ and part of its success. There's also trade-off between safety and correctness. You will see an example for that. I mean, a lot of the time, more safety gives you more correctness, but sometimes it's also kind of the opposite. There's a trade-off between complexity, expressivity, portability, and also for many companies, cost. So here's all the safeties. And as we know, C++ doesn't have any of those, right? So you can also see this as a rough list of like all the different types of undefined behavior that you can get in C++. And so why is it there? And can we maybe get rid of it? So let's look at memory safety first, and specifically type safety. That's a good place to start. So type safety is basically something where you can't have a pointer or reference to one type and then use that to access an object of a different type, right? Obviously in C++, you can do that, right? So here's some code. This is fun. So we have a class widget and a completely unrelated class gizmo. They don't inherit from each other or anything like that. And then we just cast a pointer to gizmo to a pointer to widget and just call that function there. Is this going to compile? Yep. So this like ccast is folds back to a reinterpret cast if all the other casts fail. So please never write ccasts because of that reason. It's a hidden reinterpret cast. Okay, so it's going to compile. What is it going to do? Sorry, what? Print gizmo, says Matt Godbold. Well, let's see. On Clang, yes, it's going to print gizmo. On GCC, it's going to optimize out your whole program. Because it says, well, you can't do that. So I'm going to just optimize out all code paths leading to this line of code because it's UB, therefore it can't happen, right? So it's really, really important to remember that undefined behavior is not an error. Undefined behavior means that the compiler is going to assume that it's just never going to happen because it's impossible, and then optimize based on that assumption. And then you get whatever you get. That's what undefined behavior is. And so here's another very famous example for type punning. This is the famous Quake 3 fast inverse square root from the 90s, where we have this like really clever trick that we type pun a float to an int and do some magic and then type pun back. And that is also undefined behavior, right? So that code now happens to work today, but maybe it's not going to work tomorrow. I haven't seen this particular type of code crash, but I've seen other type of code where you did similar type puns actually crash after a compiler update. So that's the thing. So now in C++20, since C++20, we do have a safe way of doing this, right? You can do bitcast, which is going to compile down to the exact same instructions on all 3 compilers that I tried. And it's not UB, right? So that's a good thing. I have a whole talk just about this. It's a few years old, but you can check it out if you haven't seen it. So what do safe languages do? Well, in safe languages, there is no way to express type punning, right? You just can't do it. And that's a pretty straightforward way to solve it, except that if you do this in C++, a lot of code will break, right? A lot of existing code which works is going to stop compiling. And that's not really an option for many people. So bound safety, right? So let's observe that in C++ we can do something like this. We can just get a number from pretty much anywhere and then use that to index into an array or a vector or anything, right? And if that happens to be out of bounds, we get undefined behavior because it's not checked. We have a safe API, right, vector.at, but we don't have to use that. And here's another piece of code. This is a row loop that loops over the vector, and if you got all the indices and the size right and the size has the correct value, it's fine. But if it doesn't, if you made a mistake, you might again have an out of bounds access. And actually funny, so this kind of stuff, actually today, static analyzers are actually very, very good at capturing this, right? If you just write plain code, you might run into things like that. But if you use a static analyzer, then typically, a lot of these cases are going to be caught. So the funny thing that I wanted to tell just now is that when I was preparing this talk yesterday, I'm going to show some data later about a survey that I did, and I was processing that data, and obviously did that in C++. So I was writing some code in C-line, and C-line has static analysis built in, so we have a data flow analysis. And so it was actually pointing out to me as I was writing the code, well, you made a mistake here, there's an endless loop. And I was like, well, this looks right. Why is this an endless loop? So I had to loop the other way around because the y-axis goes up, but I wanted to, anyway, it doesn't matter. So this looks right, but it's an endless loop because, in the inner loop, I used the wrong loop variable, right? And so here, C-line told me what was going wrong because, the sizes, everything was static, right? So the static analysis tool can see through your code and tell you what's going wrong. But if the sizes of those arrays would have been runtime values that come from some file or whatever, then no static analysis tool can tell you, right? And then you might run into undefined behavior if you don't get it right. So in safe languages, you can't switch off this bound checking, right? You don't have operator square bracket, which is unchecked. And you also don't have C++ style iterators, right, with which you can do this kind of unsafe looping. And so how does this actually work? There was a brilliant talk by Barry Revzin from CPP Paris a couple of years ago. I think it was even the keynote, where he basically compares the iterator model from different languages. And it turns out, well, in C++, we have these 3 operations. We kind of increment, then compare, argue at the end, and then dereference and read. And those are 3 separate things that you can do separately. And then if you do it all manually, if you get it wrong, you get it wrong, and then you get UB. And it turns out that in memory-safe languages like Rust, those 3 operations are kind of fused together, right? And so you can't get it wrong. So it's a great talk. And it turns out you can actually do something very similar in C++. And there's going to be a talk tomorrow by Tristan about that. So please check it out. I'm very much looking forward to that talk. So you can do it safely. But if you do that, well, you don't get iterators. You don't get random access, not in the way that you get in C++. And you can't really write a row loop over something like a container either, right? It just doesn't work. So if you have any kind of algorithm that uses row loops, like a sorting algorithm or whatever, you can't compile that algorithm in a memory-safe language like Rust. You can't even rewrite it. You have to basically redesign the whole algorithm from scratch. You can't reuse any of that code. You have to rethink how you do this, right? Because you can't express things like random access in the same way, or loops or iterators, right? So we can do it safely, but basically that means we have to rewrite all our code. And now there's lifetime safety, and this is probably the one where you can find the most kind of code examples out there doing some stuff. There's like probably one of the most common developer mistakes is returning a reference to a local variable. You can also dereference a null pointer, very common. You can do something a little bit more subtle. You keep a reference to an element in a container, and then you move from that container, and then the reference is dangling. You can do something even more subtle, right? You can modify the container while you loop through it, and then if it happens to relocate your storage in the middle, you get UB. Again, this is something that static analysis tools are actually really, really good at catching these days. So here's another example from C-Line's data flow analysis, but I'm sure other static analysis tools would give you something similar, right? So there's like always with static analysis, there's local and global. So this is an example where you do local static analysis, and the tool can see that you push back into a vector that might invalidate iterators, and so you shouldn't use the iterator afterwards, right? There's also global data flow analysis. So for example, if you have a pointer and then you delete the object, and this delete pointer function might be in a different file somewhere, but if the tool can see it, it can tell you, well, but you have deleted it there, so you can't use it here, right? It might point to deallocated memory. But of course, if the definition of delete pointer is not accessible to the data flow analysis, then there's nothing the tool can do, right? And so, tools are really good at catching this stuff, but they don't catch all the cases. And so how do we catch all the cases? Well, it turns out, as far as I know, there is exactly 3 ways to guarantee this property of lifetime safety, right? You can either track the lifetime of all objects globally, and then you end up with something like a garbage collector. That's what Java does, and C# and many other languages. That obviously has significant runtime overhead and other trade-offs, right? Like you can't do low latency real-time programming with it. There's other trade-offs. Or you can dynamically track all memory accesses. This is what address sanitizer does, right? But obviously then that's an even higher runtime cost. So it's typically not feasible to do this in production because it just makes your code more slow than what's acceptable. There are examples where you might want to pay that cost because the safety from dynamically tracking all the memory accesses is so important that you don't care about the runtime overhead. An example that I found out about recently was this iBoot thing, where Apple basically created their own dialect of C to use in iBoot, where basically every pointer is like a fat pointer, and they track basically all the memory accesses through all pointers. Actually, there's a fantastic blog post by somebody who then kind of reverse engineered that and actually writes about how this is working under the hood. So that's really cool stuff. So that's an example where you might want to do this kind of stuff even in production. But for many use cases, you can't really pay that cost. And then the third option is to statically enforce restrictions on object references by the way the language is constructed, right? Like by construction. And kind of what you want is you want to allow to have only ever either one mutable reference to an object, or one or more immutable references to an object, but never both at the same time. Right? So you can never have two mutable references or immutable references and an immutable references. That's just, if you have a language that just doesn't allow you to do that, then you can also guarantee lifetime safety. And so Rust does that famously with its borrow checker. That's exactly what it ensures. Val, one of these recent kind of languages that are in development, has a narrow definition of this, right? So it has this concept of mutable value semantics. That's the work of Dave Abrahams and Timur Doumler. We had a CPcast episode about that, really fascinating stuff. And then you can do it, make it even narrower and do what functional languages do and just not allow mutation, right? And then you're also good. And you can do that, right? Rust does that. But it turns out that if you have to program with this property, it leads to a very different programming style. And so again, a little bit like what we saw with the kind of out of bounds access and not having iterators, not having loops, many algorithmic data structures are actually inexpressible if you have to work with these restrictions, right? You cannot implement a doubly linked list in safe Rust. It's just not possible. So what you have to do if you want to write like real-world programs in general is you need to have these places where for certain things you have an escape hatch, right? Like Rust's unsafe. You just need that, right? But for kind of most code, this approach works if you can write your code that way. And so a lot of people have looked into, well, can't we do this for C++? Wouldn't that be cool if you just have something like a borrow checker in C++? So there is a paper by folks from Google. They tried to do this. It's also a very interesting piece of work. And basically the summary was, you can't. In C++, you can't implement a borrow checker because the way the language is designed, it just doesn't let you do that. And so here's kind of maybe a way to make this clearer why that is. So let's say we have a pointer to a widget, right? That's unsafe. So we can replace it with a unique pointer. Okay, that's great, that's safe, right? As we mentioned earlier, unique pointer does have parts of its API that are unsafe, like release. Right? Release gives you a raw pointer. So we can ban that, right? We can say, well, unique and release and get and those, we're just going to remove them from the API. But in order for unique pointer to be useful, you still have to be able to access that object, right? So how do you access an object if you have a unique pointer to it? Dereference, right? So you dereference it, right? And so what does the dereference operator do? It returns a reference, right? That's why it's called a dereference. So you can just call the operator and you have a reference to the object, right? And so that's exactly what we wanted to prevent. In order to basically design the language such that you can't do this, you basically have to redesign how operators and references work in C++. And that's going to just break all code, right? So you just can't do that. Actually, interestingly, Sean Baxter, the developer of Circle, tweeted a few months ago that he is actually implementing a borrow checker on top of C++. So I'm actually really curious how this is going to work, because from everything I've read, you can't do it. But let's see. I'm very curious. I think so far nothing public has come out of this. But yeah, I'm very curious. Maybe he's going to prove everybody wrong. So yes, borrow checker. We're going to talk about this a little bit more later. But now let's talk about initialization safety. That's the last type of memory safety here on my list. And I did a talk about just initialization actually here on the stage 4 years ago. The most recent version of that talk is from Meeting C++. And so that's another problem in C++. You can just not initialize a variable and then use it. So that variable is going to have an indeterminate value, and reading an indeterminate value is ub. And so if use I just writes something into I, you're good. But if it reads from I, then you're toast, right? So here's a slightly more subtle example. It's a struct that has a char and a size t, and then you initialize it, right? Here's an aggregate initialization, everything's good, you initialize it, and then it's trivially copyable, right? And so you just memcopy it. What's the bug here? Yes, there's some padding bits. Because of alignment, you have like some bits between C and I, and those are not initialized. You didn't initialize them. And so you're reading uninitialized memory, and again, that's UB. So, in a safe language, we have two ways of avoiding that. We can just say, you must initialize all variables, otherwise it's a compiler error. Or we can implicitly initialize a variable to some kind of default value, like for numbers, it would probably be 0, etc. And so it turns out, well, we can do that in a different language, but we can't really enforce explicit initialization in C++, because that will, again, break all code. And it turns out we can't really implicitly initialize a value either, because that kind of might actually, there's different trade-offs here. There is a performance trade-off, right? So maybe with one int, it doesn't matter, but like an array of ints you don't want to pay for the initialization, right, in some cases. So you need an escape hatch to not initialize them. And the other problem is with correctness, right? If you initialize everything to 0 by default, 0 might not be the correct value. For example, on Linux, I think the user ID 0 means root. That's probably not the number that you want to initialize it to by default. And so if you have that bug in your code and you say, well, it's just going to be initialized to 0, you're going to mask that bug. And static analysis tool, again, it's very good at finding these cases where you didn't initialize something, but it's not going to find that anymore if it's not a bug, right? If it's just silently turned to 0. There's all of these trade-offs here. So there is this paper by JF who proposes to 0 initialize objects by default. And yeah, now we're looking at this in the committee, and there's all these trade-offs, right? There's the correctness trade-off, there's the performance trade-off, you need some kind of escape hatch. There was a response paper by Thomas Köppe to say, well, we do it slightly differently. We initialize it to some kind of defined value, which is not necessarily 0, but then it's still an error to read from it. And then there's another paper which is actually comparing all of these approaches, and you see, it gets really complex. There's like all of these trade-offs here. It's not obvious, if there is a clean way of like fixing this particular type of UB. Maybe there is. We're working on this on the committee. We're going to hopefully figure this out, but it's not obvious at all. Like if you already have a language that does it the way C++ does, retrofitting a solution into it is highly non-trivial if you want to keep all of those trade-offs in mind. Okay, and now there's thread safety. So it turns out in C++, nothing prevents you from doing something like this, right? You have a variable, and you write into it from a thread, and you write into it from another thread as well, right? And that's a data race, that's undefined behavior. Your compiler is allowed to optimize based on the assumption that this is never going to happen, and you're going to get very weird things. In practice, this actually does happen. For example, I've seen this a lot in music software, where you have some kind of like, gain. Sorry, I'm skipping ahead here. You have gain, for example. You have some kind of like, volume knob, right? And you have a GUI, and if you turn the knob, it's going to increase the volume, and then you have a process which runs on the processing thread, which is a separate thread, which is going to like use that value to generate sound, right? So it's going to multiply the signal with that gain. And then if you have both threads accessing that value, that's a race condition. And so probably on x86 this is going to be fine, but in general, that's not safe. And so some people say, well, let's make it volatile. It gets rid of some of the evil optimizations that the compiler is allowed to do, but it's still undefined behavior. So what you have to do is you have to make it atomic, right? But the problem in C++ is that nothing forces you to do that. You kind of have to know that you have to do that. Right? And that's the thing that makes it unsafe. And so safe languages deal with this problem in various different ways. There's the Java model, which is basically saying everything's sequentially consistent. There are no data races that are undefined behavior, but you get what you get, right? You might get like torn reads, torn writes, inconsistent values, but it's kind of undefined behavior, but it's bounded undefined behavior in the sense that if you have a data race in Java program, you might read garbage values, but you're not going to bring down the VM, right? So it's kind of like the damage you can do is limited. And the other model is, again, the borrow checker, which works just as well for threads, where you basically say you follow the same model of only having one mutable reference or multiple immutable references. And that's how you share data between threads. And then you basically can't have data races, right? Because you can't have two threads trying to access the same data simultaneously and one of them writing, which is what a race condition is. So you just can't have it by construction. And then again, in functional languages, you can't have them because you don't have mutation at all, right? And so this model is really, really beautiful. This is something somebody on Reddit wrote that I thought was really good. Rust will not let me send any data to another thread if it's not entirely safe, thread safe. If I try, it will point out exactly which field or which struct needs to be wrapped in atomic or in mutex. It will not allow any code anywhere touch that data without proper synchronization or a compile time guarantee that no other threads can see it. This works across entire code bases, including third-party dependencies. Well, it's great. Unfortunately, we can't have it in C++. So what can we do in C++? Well, we have thread sanitizer, which finds some some things, but it typically only finds races that happen while you actually run it. It also masks some races because it introduces new synchronization points. There are cases that it just can't capture. Like, for example, if you have one thread that creates an object, placement moves it into a buffer, and then another thread kind of reads from that buffer, or anything else that involves some kind of side channel, thread center is not going to find that. So there was this tool which JF, I think, told me about, or was it Andreas? I don't remember. One of the two of you told me about this. There was this really clever tool which is called a Jinx debugger, which can kind of deterministically interleave your threads and kind of go through all the combinations and then kind of find race conditions that way. But it's been discontinued, and I don't know why it's not apparently become a massive success. Maybe for some reason this is not a scalable approach. So the only kind of more or less reliable way we have to track down race conditions in C++ is with annotations, right? There's something in Clang, but like there was a question, I've heard some people say maybe that doesn't quite scale to big code bases. I don't personally know. I'm kind of curious to know if that approach scales. And we have arithmetic safety. So signed integer overflow is undefined behavior in C++, and that leads to some hilarious examples of UB. So here we have a loop, and the compiler knows that it cannot overflow, and it can optimize based on that assumption, right? So what it can do is it can eliminate the variable e and move I and move that kind of number out of the loop. Then it can say, well, that's bigger than max int, so that's always true. And then you get an infinite loop. So in safe languages, you can do other things. You can trap, panic, or throw an exception. Like in Java, by default, you fall back to some kind of defined behavior. I think Java wraps around. But then you have the option to instead throw in exceptions. In Rust, in debug, it's going to panic, and in release, it's going to wrap around. Unsigned undefined behavior is actually not UB. And most of the time it's a bug, but I've seen cases where it's not. Like there's a crypto people use it apparently, and I've seen a use case in graphics where you kind of exploit unsigned integer overflow. So yeah, it's often a bug, but static analysis tool sometimes can't tell. And the last one here on my list is definition safety. That's the one that isn't really talked about that much in that context, but I think it's important. And that's stuff like ODR violations, ill-formed NDR, right? You have like two different definitions of the same struct in your program, and then you get really nasty and difficult to debug undefined behavior. And I think modules fix that, right? Daniela nods. So when we get modules kind of across the ecosystem, we're gonna finally not have to worry about that. But until then, we have to deal with it because that's just an artifact of how linkers work, right? So if you don't have linkers in the way C++ linkers work, you don't run into that problem. So where are we with all of this stuff? C++ has a lot of UB, right? Some of it can be diagnosed at compile time, static analysis. Some can't. Some of it can be coded at runtime. Some can't. Some of it can be avoided by using higher level abstractions. This is, I think, my favorite example. Mutexes are unsafe, but you can put stuff on top, like boost unsynchronized value or libguarded. Thank you very much, Barbara and Ansel. Great library. But there's no switch that forces you to do these things, right? You can always fall back to the unsafe thing, and there's nothing in the language that prevents you from doing that. Some of the stuff can be fixed by evolving the C++ standard itself, right? So we can make things that were previously UB either well-defined or ill-formed, but we have to keep in mind these trade-offs. We can't just use that for everything because then we're just going to break everybody's code, and you have to write your code in very, very different ways, and it would be basically equivalent to writing it in a new language like Rust, right? And some of it we just can't fix because of the way C++ language is designed. So I think this is kind of my first kind of thesis of this talk, is that you cannot actually completely eliminate UB from C++. Just can't do it. Security experts saying, well, we have actually not addressed safety until we have eliminated all UB, which, fair point. They're probably right. And that leads me to a corollary C++ will never be a safe language, right? That's just the conclusion. Does it really matter? Well, the good news is that we can mitigate a lot of this UB, right? We can write tests, we can aim for very good test coverage, we can have fuzzing, we can have coding guidelines. Lots of people in safety critical code industries use things like MISRA or other coding guidelines, and it's kind of regulated. So we have static analysis tools that know about these coding guidelines and can enforce them to a reasonable degree. We can have mandated code reviews. We have very good static analysis tools. We have sanitisers. One person who is a very senior person in a safety critical industry says, this works for us. This was a hallway discussion in some conference recently. This works for us. We don't have to move away from C++. Somebody else says, well, companies get hacked because of vulnerabilities in network libraries. Those are written by people who don't apply these good engineering practices. That is the actual problem. So, that is one side of the story. The other side of the story is that security experts are saying, well, unit tests don't cover everything because they're not written with exploits in mind. They target unintended failure, not a smart attacker. Fuzzing has not reduced the number of exploits measurably. Coding guidelines and static analysis is not a comprehensive solution because whenever you write code, you write bugs. And they don't catch all the bugs. And if they do catch a bug, you write more code to address the bugs, so you introduce more bugs. Right? Sanitisers typically are not deployed in production because of runtime overhead. And with all of these tools, we don't have a standard set of them, right? We don't have a set of, say, use these tools and then you're going to be this much safer. That standard doesn't exist across the C++ ecosystem. And with threat safety, data erasers is typically not caught by any of those tools. So that's really very difficult. Well, there isn't really such a thing as safe code, is there, right? So safe programming languages still have to call into unsafe ones. There was a delightful discussion somewhere on the internet about Rust people trying to figure out how to read an environment variable. You have to call into a C API, which is inherently unsafe. Right? So you have to kind of wrap it with some kind of high-level abstraction that does something slightly different. All programming languages actually have vulnerabilities and exploits, right? So Rust has vulnerabilities, probably a lot fewer than C++, but it has vulnerabilities. Java has vulnerabilities. There are vulnerabilities like Spectre and Meltdown, which are actually on the hardware level, right? And so the current debate, I don't think at all is about making all code safe. It's about kind of removing or reducing those about 70% of vulnerabilities that are due to the memory unsafety issues in C++, right? But okay, so I looked at some numbers, like Google had an article about this, where if you start introducing more and more memory-safe languages, you obviously reduce the number of memory safety vulnerabilities. That's pretty obvious. But it's unclear that it's actually going to remove 70% of all vulnerabilities, right? Because attackers are kind of like a gas, like they fill all the volume that is available to them. So it becomes like a game of whack-a-mole, right? If you remove the cause for 70% of the vulnerabilities, attackers will go somewhere else and find something else to exploit, right? So I haven't really seen, maybe it exists somewhere, like a good study of like, if we do this, what actually happens to the number of vulnerabilities overall, not just the ones that we remove. Should we care about this? Well, there is a spectrum, right? There are quite a lot of people who are saying, this is an existential threat to C++. And for a lot of people, this is probably true. But then there's also a lot of people who say, well, this is not relevant to us, right? And so there is kind of a distribution of people somewhere on this spectrum, right? And I think that governments around the world might introduce some regulation. It's likely to happen in some form or another, and probably that distribution is then going to change. But right now there is a certain distribution, but it's not like every C++ developer in the world is on the left side, right? And it kind of depends, how safety critical is your code, right? Some code, human lives depend on it, and we need to take that very, very seriously. Some code, well, if it crashes, well, it's unfortunate, but we don't really care. Like, time to market is a lot more important, in some industries than not having crashes. And so, there are certainly, differences between industries here. And another concern is, how many users do we have, and who are they? right? So if you're, for example, doing a scientific simulation somewhere in academia, you're the only user, right? If it crashes, you're just going to run it again. Another interesting thing happened if you do like low latency trading, for example. There are essentially no hostile actors, right? No one is trying to exploit undefined behavior in the code because everybody's going through the same exchange. Everything's monitored, right? So if you do something dodgy, then probably the following week you'll have heavily armed FBI agents at your door. But like UB is not really something that, like it's not that you have to code with, attackers in mind, right? What you care about is performance, 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 and correctness. And in music software, which is something I've been working on for a decade, the only time I have come across like safety concerns is when people try to hack your copy protection. But that's an entirely different problem, right? They have your binary there, so they can manipulate your binary in whichever way they want to kind of circumvent that copy protection, right? So it doesn't really matter what programming language you write this in. So it's kind of orthogonal to UB. And there are all these trade-offs, right? So safety is important, and it's very, very important for some industries. It's maybe less important for others. But if you want to increase safety, we have to keep all of these trade-offs in mind. And one particular trade-off that I want to mention is performance, which is something that is dear to my heart because of my background. And here's like 2 data points. This is something that I heard from a low latency trading person. Placement new used to have a null pointer check in it, and for some reason in their code, it didn't get optimized out, and that slowdown from this one check was unacceptably slow in that use case. It was just not acceptable for them, right? So they'd have to like hack the compiler to like not insert the check, and then eventually we had a defect report to make it UB in the standard. Here's another example from high performance computing. The people use complex numbers a lot, but stat complex forces you to zero initialize the values or initialize them to something, right? It does not allow you to just leave them uninitialized. And for HPC people, that's an unacceptable performance overhead. So they just don't use stat complex. They just don't. They roll their own. It's going to be very, very interesting when SIMD comes around in C++26 and they find out that they can't use their hand-rolled stat complex with SIMD. That's going to be very interesting. So here's my second thesis. Compromising on performance is at least as much of a threat to C++ as the current safety debate. That's a very subjective opinion, but I believe that's the case because performance is the reason a lot of people do C++, right? And C++ lets you reason about the performance of your code in a way that no other high language does. If safety is your primary concern, there are alternatives like Rust. And so here's another question that people ask a lot. Is C++ doomed unless you make it a memory-safe language? And here's my third and last thesis. I don't think so. Unless there is like government regulation outright forbidding you to write C++, I don't think it's going to go anywhere. I saw a number somewhere that something like 20% of all code in the world is C++. I'm not sure where that number comes from or if it's correct. Maybe somebody knows. So I did a little thing. I'm actually thinking maybe I should do that as a lightning talk because I'm running out of time here very quickly. How much time do I have left? 5 minutes. 7 minutes. Okay, well, let me whiz through this very quickly. So I was kind of looking, to what extent is undefined behavior in C++ today actually perceived as a problem? So I collected some data. Right? I did a survey. 580 people participated. Thank you very much to everybody who did. I asked 2 questions. How much effort do you spend mitigating UB? And how much, basically, how much negative impact do you experience from the UB that you failed to mitigate? And then the third question was, what industry do you work in? And so here are the responses. About 2/3 of the people say, well, I spent either none or some effort mitigating UB. And 1/3 of people says, significant or huge effort. And then how much negative impact do you experience from unmitigated UB? And here about 3/4 of people said, well, none or some. And only 1/4 of people said significant or huge impact. And so I kind of correlated that. And there was this kind of distribution here where the majority of people live in this happy quadrant. They don't have to spend that much effort to mitigate UB, and they don't really have much damage from UB in production. Then we have 22% 90% of people in this quadrant where they say, well, we have to actually spend a lot of effort mitigating it, but then we're good. 11% of people say, well, we don't spend as much effort mitigating it and we're suffering from it. So, really these people should just do a better job mitigating their UB. And then we have 11% of people in this really unhappy quadrant that are saying, well, we are trying really hard to mitigate it, but we're still very much negatively affected by it. So that's the quadrant where people maybe C++ is not the right solution for them, or maybe they should do something differently. Maybe there are other mitigations that they should use that they're not using. And so I also actually then did this per industry. So I said, okay, this is the overall distribution. Let's look at just people who said, they work in a safety critical industry like automotive, medical, aeronautics, military. Actually, quite a few people from the military industry filled out the survey. I was kind of surprised by that. And I get essentially the same distribution. And then I looked at people who work in industries where I was pretty sure they're not safety critical, like games, music, software, education. And I got pretty much the exact same distribution. So I found that very curious. So my conclusion from this is that today, C++ developers generally do not perceive undefined behavior as a business critical problem. Now, whether they're right, that's a different question, but they don't perceive it as a business critical problem. So maybe everything's okay. Well, for some people it is. For some people it's not. I would say if you need guaranteed memory safety, you write everything in Rust. Obviously, that's a problem. A lot of people don't want to write Rust, or you can't afford to do that, right? Because something like Unreal Engine or Juice, for example, like very big, like in music software, just doesn't exist in Rust at the moment. So it's prohibitively expensive, to rewrite everything in Rust for many, many people. So what alternatives do we have? We have these new C++ successor languages that we have talked about a lot recently. They're not mature, so either they have like very good interop with C++, but they're not actually fully memory safe, or at least not at the moment, like CPP2 and Carbon, or Val is, but C++ interop isn't really part of the story there. Rust is pretty much the only one of these that is really reasonably mature, so maybe we should just invest in C++ Rust interop. I think that's a very reasonable thing to do. We have formal proofs and provable languages and all of that stuff. It works for small self-contained problems, right? So I was talking to some automotive people and they said, well, we do this model in MATLAB, we have a formal verification, then we generate the C code, and it works as long as the system is really small, like kind of the program that triggers the airbag. But as soon as it's the lights, it's already too complicated, right? We can't use it there. So maybe one day we will get memory checking in hardware. That would be awesome. I don't think we're there yet. So what we can do is we can evolve C++, right? We can mitigate UB in cases where the trade-offs are right. And we've been doing this for a long time. And this is an ongoing effort, right? So there was J.F. Bastian's bitcast papers. Now we can do type punning safely. We have implicit creation of objects. So you can just cast the memory buffer to some object. And depending on like if the type has certain properties, then it's just going to create an object magically for you. So it's no longer UB. In C++ 23, we fixed the range-based for loop. We have start lifetime as. And there's ongoing work, right? So there's already, I mentioned the ongoing work due to uninitialized values by J.F. Bastian, Thomas Körper, and others. There's another paper from JF to remove UB due to trivial infinite loops, which is also ongoing work. I'm working on a paper to remove UB when you read the underlying bytes of an object, because it turns out that's also UB, even though it shouldn't be. So you can't essentially implement a hex editor unless you memcopy everything. There's work on lifetime annotations, and there's this big effort to get contracts into the language, which is also targeting safety. So that's a big, big topic. Can't go into this now because I'm running out of time, and also this is a whole other talk. This next talk I'm going to give. And yeah, so that's something that we're doing. I just want to very, very quickly in the last minute here mention that there is also ongoing work by Bjarne Strustrup and others. There was this opinion paper by the Direction Group. Bjarne wrote this paper, and there's some discussion there where he says, well, C++ is actually as safe as Rust. That material wasn't very well received by the community, to put it mildly. There were lots of reactions like this. I kind of was a bit surprised by this disconnect, so I tried to figure out what's going on there. I have like 30 seconds left, I think, so I'm not going to go into this. But basically, Bjarne's approach is actually really interesting. I think it's kind of misunderstood. I want to understand this more, so I hope that Phil and I can get him on the show at cppcast, and we can talk to him about this in more detail. So, and this is my last slide. the billion-dollar question really here is, with the work that Bjarne is doing and that some other people are doing, does a subset of a superset, which is kind of Bjarne's approach, exist that achieves similar guarantees to Rust, is useful and expressive enough, and is compatible enough with today's C++? And that's kind of the question that they're trying to answer. And if the answer to this is yes, that would be awesome, right? Because that would solve a lot of these problems in much better ways than rewrite everything in Rust, which is prohibitively expensive for many people. But the problem is that nobody knows the answer yet. And from what my feeling is that the answer is probably no. And so here's my conclusion. In my opinion, and this is again subjective and we can discuss it later, but I don't think we can eliminate all UB from C++. What we can do is we can gradually remove some of the UB when the trade-offs are right, and we are actively working on this on the committee. But we shouldn't compromise performance and compatibility to do that. I don't think C++ is doomed. I think a lot of this is actually just a PR problem mostly, but it's kind of our own fault on the committee. We should communicate the strategy clearer. It's like, we're not trying to do this, we're trying to do that, and this is why, and this is how, and these are the things that we're doing. And if we could communicate that clearly, I think a lot of this PR noise would kind of go away because we could have like a reasonable conversation. There wouldn't be this disconnect. And if you need guaranteed memory safety by construction, use Rust. And that's it. Thank you very much.